An important distribution in econometrics and statistics is the chi-square distribution. And just like the normal distribution, it's actually a family of distributions. One of the distributions in this family is called the chi-square with 1 degree of freedom, or chi-square 1. And that is fairly simple to define. So the chi-square with 1 degree of freedom is simply defined as the square of a standard normal. If you want to simulate a random number from the standard normal, then you can just do from Excel, you can just do as we have done a couple of times, equal to norm dot, and you can actually do S because it's standard normal, a little bit quicker, imb and rand, and you don't have to do the arguments 1 and 0. So this is one random drawing from the standard normal. Let's just remove a couple of decimals like this, and if I F9, we know a little bit about the property of the standard normal. Its expected value is 0, its variance is 1. There's about a 95% probability of getting a number between plus minus 196, for example. So using that, we can simulate a random number from the chi-square simply by taking the square of b1. So if I do b1 square, this is going to be a simulated random number from the chi-square 1 distribution. So let's focus on this one now in b2 and have a look at that. We see that the random numbers from chi-square 1 degree of freedom must obviously be positive because we're taking the square of a number. What's not so easy to see is that these random numbers in cell B2 are actually drawings from a random variable with expected value 1. So if you took the average of all these numbers you see in B2, then it will eventually converge to 1 if you do this enough times. Maple is a nice place to go if you want to learn a little bit more about the chi-square 1 degree chi-square distribution. So we can just do with statistics, and then we can define a random variable x equal to colon equal to random variable, and we can do a standard normal 1001 like this, and Maple will actually allow you to do the functions of random variables. So I can do, for example, z as the square of x. So now z will follow a chi-square with 1 degree of freedom. You can see exactly what the probability density function is for the chi-square 1 simply by typing PDF z, z, for example. Then you see that it's a little bit complex, but it's 0 when z is less than or equal to 0. Well, we realize that you cannot get a negative number if you square something. And then it has this little bit more complicated form when z is greater than 0. It's not at all important to remember this PDF, but it is nice to remember at least a little bit about how the PDF looks. So if we do a plot of the PDF z, z for, say, z between 0 and 3, then this is what we see. Well, that's not so cute because it goes to infinity as z goes to 0. So let's add for the y-axis y equal to 0. Let's just plot it to up to 2. That's a little bit better. So most of the mass is located here for very small values of z, and then for larger z's the probability will decrease. We can find the expected value of z. But before we do that, notice that you can create a chi-square distribution straight away in Maple without squaring a normal. So I could also do y colon equal to random variable and do a chi-square, and then you put 1 inside parentheses for 1 degree of freedom. If you want to know the expected value, the chi-square, just do the mean, and you see that it has the expected value of 1. That is, if you think about this graph here, then 1 is at the center of gravity. This is where it balances completely. Even though it goes to infinity here, it also goes to infinity up here, so it will be the expected value. It has a variance of 2, which we can confirm by doing this. And we said before that the chi-square distribution is a family of distribution. Chi-square 1 is just one of them. So let's have a look at the other ones. So first of all, this is the notation that we use for the chi-square with 1 degree of freedom. We write a chi symbol, degree chi, put a 2 as a superscript and 1 as a subscript. Chi-square with 1 degree of freedom. If I have instead k independent random variables, z1 through zk, and they are all normal 0, 1. They're all standard normal, and they're all independent. Then the sum of squares of these guys, the sum of squares of the z variables, they follow something called a chi-square with k degrees of freedom. If you want to simulate random numbers from a chi-square with k degrees of freedom, what you can do is, let's say you want to do it for k equal to 5. Then just simulate standard normal here, like this. Copy this down for k times. So if you want to do chi-square 5, now I have 5 independent drawings from standard normal, and then just do the sum of squares. Sum SQ of these guys is this one is a drawing from a chi-square with 5 degrees of freedom. Since it's sum of squares of 5 instead of 1, the drawings from chi-square 5 tend to be bigger than the chi-square 1. And indeed, this one has an expected value of exactly 5. It will always be the particular value of k. If you want to have a look at chi-square distributions for other values of k, you can easily do that by just changing this to, let's say, 5. You can see now that the expected value is 5, like we said, and the variance turns out to be always precisely twice the value of this degree of freedom 5. So the variance will be 10 in this case. We can also plot it. If I just change this to y random variable, let's just do it as a function of z again. Then we see what it looks like. And now I need to extend it beyond 2 because the expected value is, beyond 3 because the expected value is now 5. So I don't need to impose restrictions on the y-axis anymore, so let's extend it to 9. Or a little bit more than that. We can see the tail also. So this is what the chi-square distribution with 5 degrees of freedom looks like. And there's one thing that you should pay attention to, and that is the skewness. We say that this is skewed to the right. It's certainly not symmetric around its maximum. And you can also see that the point, the z value that maximizes the PDF is not the expected value. The expected value is right here. And that's the center of gravity for this distribution. And the principle is simply that if you increase the degrees of freedom from 5 to something higher, then the distribution will look more like this instead. The The maximum will be shifted to the right and it'll be a little bit more skewed to the right. One thing we need to know is how to calculate probabilities from the chi-square distribution. There are lots of ways of doing that. For example, you can use Excel or you can use a table. So just to give you a simple example, let's say I have a random variable that follows a chi-square distribution with 5 degrees of freedom, and I want to know the probability that y is, I don't know, greater than 8, let's say. Excel has two functions that can help you. It has the chi-square dist that will calculate probabilities such as the probability that y is less than 8. Less than 8. That is on the left-hand tail. But it also has another one which is chi-square dist RT, where RT stands for right-hand tail. So this will calculate probabilities such as this one, that y is greater than a number, than a specific number such as 8. So that's the one we can use. So we just then put our value here, 8, and then we put the degrees of freedom, which was 5 in my example. So this will give me the probability that y is greater than 8, and it turns out to be about 15.6%. But of course you could use the chi-square, you could use the chi-sq dist as well, and then do it from the number, and then the number you will get, you just take 1 minus that to get the result. In statistics and econometrics, the problem we're facing is almost always the opposite. That is, I know the probability, let's say 0.05, but I don't know what value I should put here. That is, I know the distribution looks something like this. I know that I want 5% in this tail, and the question is, what's that number then? So it's the inverse problem of the other problem. You can do that as well in Excel. So we can, in this case, we can just do equal to chi, and then we use the chi-sq-imb. And we again use the right-hand tail because I want to write the probability of the right-hand tail. So if I put 0.05 here and my degrees of freedom 5, I find the answer, which is 11.07. So 11.07 is the right answer. The probability getting a number greater than 11.07 is precisely 5%. And there are many other ways of doing this. You could, for example, use a table. Most tables do plot the right-hand tail of the distribution because that's the most often that's the ones we're after. So for example, using the table, you can find degrees of freedom 5 here, and if we're looking for 95%, sorry, it's right-hand tail, so we're looking for 5%, just like that. We see that we get the number 1107, which is, yes, the same we got from Excel. Note that the table in general can't answer questions like that. The table can only answer the inverse problems. That is, when we know the probability, and the probability is one of these common ones, then we can use the table. You can use Gretel to find these values by going to Tools, Statistical Tables, the chi-square. So we put degrees of freedom 5 and the right-hand probability to 5%, and hopefully that will give us also the same number, 11.07. Or you could use eViews by simply typing in the command window. So the first thing you'll do is you'll type coef, just creating a coefficient, and call it something. Just call it A, doesn't make any difference. And then you do the @ sign, which is eView's way of saying that we're calling a function. If you want to solve this problem, with the chi-square distribution, then the function you should use is q chi-sq. So let's see, q chi-sq. Then put the probability, and it wants the probability in the left-hand tail. So 5% in the right, 95% in the left. Then 5 degrees of freedom, and you can see that A popped up right there, and it has a little beta symbol next to it. That just means that it is a coefficient. It's not a data series or regression, just a simple coefficient. So we can see the value of it, 11.07, or if you want to do that, you can also do the show command. Not the how, but the show A, and it pops up. Just check out the statistical distribution functions here, and you can see, for example, for the chi-square, I use this one, q chi-square. Final point, if we have a random variable which is distributed with the chi-square distribution with k degrees of freedom, then this is the notation we use. We put the k as a subscript.